In this video, we're going to take some time to look at rational functions. If you think about the word rational, we usually see that when we talk about rational numbers. Rational numbers are numbers that can be written as a fraction. So these are functions that are formed as a fraction. So we have the definition here. It says a function of the form f of x equals p of x over q of x, where p of x and q of x are polynomials. So basically we're going to divide two polynomials and form a fraction. Anytime we form a fraction, mathematicians freak out a little bit about the denominator being 0. We can't divide by 0, so q of x cannot be 0. The most basic rational function is the 1 over x graph. So I thought we could take some time to look at this and look at its shape and kind of talk about all the characteristics of this graph. Okay, so I made a really large t-chart here just to give you an idea of some of the patterns that are going on for this function. Maybe first we should mention, right, what x value can we not have for y equals 1 over x. Remember we said we can't divide by 0, so x cannot be 0. And so I usually put that number right in the center here. I can't use 0, so at 0, this 1 over x function is undefined. Okay, but I want to look at what happens around 0, and I want to look at what happens at the very ends of the graph. I'm realizing here that I've left a couple of numbers out, so I put a really small decimal on the negative side, but I didn't put a really small decimal on the positive side. So maybe, can we just add that right in here? I don't know what I was thinking. Okay, and the rest of these should be the same. The only other thing is I also really want to look at a really big number, both on the positive side and on the negative side. Somehow I managed to leave that out. I'm not sure why. Okay, so we'll pencil that in too. Okay, so because x cannot be 0, we very often draw in a dotted line where x is 0 because the graph is going to get infinitely close to this line. I'm going to go ahead and draw that. So this would be the line where x equals 0. Okay, it's not actually part of the graph, it's just a guiding line to help us make the graph. All right, and then let's plug in the rest of these values. We'll come back to the really large and the really small ones. Let's fill in these in the middle. So if I put in -2, 1 over -2 would be -1/2. If I put in -1, I would get -1. 1 divided by -1/2. It's like 1 divided by 0.5, right? Should be a 2. And this one is negative. Okay, same thing on the positive side. 1 divided by +1/2 would be +2. 1 divided by 1 is 1. And 1 divided by 2 is 1/2. Okay, and then we could put in, well, should we plot those first? Or we'll just add the rest of them. Okay, so if I put in a really big number for x, like negative 1,000, I'm going to get a really, really tiny number for y. I'm going to make this one into a decimal, just to make it easier. So this would be -0.001. And if I put in a really tiny number for x, 1 divided by a really tiny number is going to give us a really big value for y. We say this is inversely proportional. So as x gets really big, y gets really small. As x gets really small, y gets really big. So they kind of have an opposite effect. If I put in this small decimal for x, I'm going to get a big y value. And if I put a really big number for x, I'm going to get a really small y value. Okay, so the graph is actually divided into two parts. We have the positive side and the negative side because it's undefined right here down the middle. So let's plot the points on the positive side first. So we have 1/2, 2, 1, 1, 2, 1/2. Okay, and I don't think we can actually plot these other tiny and very large numbers, but we can think about them. So as I get really close to 0.001, the y value is shooting up to this really large number. So that means that as I draw my graph, it's going to get infinitely close to this dotted line. Because as x gets smaller and smaller, y shoots up and gets really, really big. And as x gets really, really big, on the outskirts of this graph at the ends, the y value is getting smaller and smaller and smaller. So it's tapering off onto the x-axis here. I really should have labeled these. Okay. The same thing's happening on the negative side, and we're going to be here in quadrant 3. So I have -2, -1/2, -1, -1, -1/2, -2. And the same thing's true. If I put in a really small x value, as I get closer and closer to 0, the y value is going to get really big, this time in a negative way. It's going to go down very quickly. And as I get very big for my x value, a big negative number, my y value is getting very small, closer and closer to 0. So I drew in the, this is called a vertical asymptote. And we'll take some time to talk about what that is in a second, but it's a vertical line that the graph approaches and gets infinitely close to. And then there's also a horizontal line that the graph approaches at the ends of the graph. And for this basic one, that happens to be right on the x-axis. So there's also a horizontal asymptote where y equals 0. And that's because the y value is approaching 0 at the ends of the graph. If we think really hard, okay, about what numbers I can get out as a y value when I'm calculating with 1/x, even if I put in a really, really giant number like a million or, I don't know, a trillion or something, 1 divided by that really giant number is still going to be a really tiny infinitesimal decimal. So I'm never going to be able to get 0 itself out of this fraction. The only way I can get 0 from a fraction is if the numerator is 0, and this one's not. So the y value is also never going to be 0. But it's going to get really close. Okay, so that's why we draw in these dotted lines called asymptotes. So this is a good sort of setup for the way these functions look. We're going to delve into the parts of them. We're going to talk a lot about the vertical asymptote. We're going to talk and how to find it. We're going to talk about the horizontal asymptote and how to find it. And we're also going to talk about a hole or a missing point. Those are the 3 big characteristics for these graphs. If you wanted to add a 4th, I would say the 4th would be the domain and range. So let's take a second to jot that down for this particular graph. The domain and range are going to come really from these 2 restrictions, right? So I can put in any number I want for x except for 0. And I can get out any number I want for y except for 0. So if you match that idea up with what we see in the graph, from left to right, the domain is going to go from -infinity up to but not including 0, because I'm infinitely close right here. And then on the other side, I'm infinitely close after 0, going all the way out to infinity. So I'm just leaving out the one number, 0 itself, right? Because x cannot be 0. And the same thing's true for the range. I'm going from the bottom up. I can get any number I want up to infinitely close to 0, which would be on the x-axis. And then just after 0, all the way up to positive infinity. Okay, and so I've jotted down just a note here at the bottom about the asymptote. So a vertical asymptote, this blue dotted line that we drew, occurs when the y value, I put the absolute value bars on here, so the absolute value of y goes to infinity. That means right at the top of the graph it's going to positive infinity, the bottom of the graph it's going to negative infinity. But both of these are happening as x goes to 0, either from the right or from the left. And so that's sort of why we draw in that dotted line. And then the horizontal asymptote occurs when as x goes to infinity, I have the absolute value bars, so x gets really big either on the positive side, positive infinity, or x gets really big on the negative side, negative infinity. As these happen, the y value is leveling out at 0 for this function. And so we drew that pink dotted line so you could see it approaching 0. Okay, so let's take a look at these individual parts so you can get a better understanding of how they work. We're going to start with the vertical asymptote. So the vertical asymptote is a vertical line which the graph approaches but does not cross. It does not cross it because this is the place where the denominator would be 0, and we said that the fraction is not defined at that spot. So it's never going to cross the vertical asymptote. To find the vertical asymptote, we're going to factor and reduce the fraction. Then we're going to set the denominator, the bottom, equal to 0 and solve for x. And whatever numbers we get, there will be a vertical dotted line that we draw. Okay, and when we represent a vertical line, technically it's an x equals that number. So even though it's tempting to say the vertical asymptote is 2, right? You know, if you want to get all the phrasing right, it's better to write it as x equals 2 so that you can know that you're representing a line versus just a number. Okay, so let's take this example. Here's a function. It's a rational function because it's a fraction here. So if I wanted to find the vertical asymptote, I could factor and reduce. This example is not factorable. We're going to look at some that are in just a second. Okay, so I don't have to do the first step because I can't factor this. So then from here, I'm going to set the denominator equal to 0. I usually use VA as my abbreviation for vertical asymptote. I'm going to set the denominator equal to 0. Okay, so x equals 4 is my vertical asymptote for this function. And I printed the graph here so you could get a visual picture of this. And since it would take us a long time to draw the graphs ourselves, although we are going to do that sort of as a culmination to draw all of these things together, while we're just starting out, I wanted to give you a good picture. So 1, 2, 3, 4, right? This is a vertical like vertical blinds, okay? Here's where the vertical asymptote would be. And you can see that the graph is getting closer and closer to that vertical line towards the middle. Okay, so that's the idea. It's a dotted line because it's technically not part of the graph, but it is a guiding line to help us draw the graph. All right, so now let's look at the horizontal asymptote. So the horizontal asymptote, this is a horizontal line, horizontal like the horizon, which the graph approaches at the ends of the graph. So that makes this one a little bit different than the vertical asymptote. This is like the end behavior for the rational functions. A graph may cross its horizontal asymptote. So these graphs can take on all different kinds of shapes, and they can be split into several different parts. We're going to focus mostly on the ones that have just 2 parts, but anytime you have more than 2 parts, you get 3 parts or 4 parts, I guess you could have, or something like that. Those middle parts may cross over the horizontal asymptote, because the horizontal asymptote is not really about the middle parts, it's about the ends. So we draw that dotted line because we want to be able to figure out where the ends are going to taper off or level out. There's a couple different ways you can find the horizontal asymptote. I found that most people like to use this 3-parted rule, so I'm going to teach that in this video. There is another method where you divide by the highest power on x, so you can go investigate that online or in the textbook if you are interested in that. I'm going to be just using this 3-part rule, just because in my experience, most people prefer this above the other. Okay, so there's really 3 options. To decide the horizontal asymptote, we can compare the degree of the numerator and the degree of the denominator. Numerator being the top, of course, the denominator being the bottom of the fraction. So they're sort of in a competition, okay? And depending on who wins or if they tie, that's sort of, you could think of it that way, that can determine what kind of horizontal asymptote or what happens at the end. So if the numerator, the degree, right, the highest exponent in the numerator is smaller than the highest exponent in the denominator, so the denominator has the bigger exponent, then as x gets really big, because we're talking about the ends of the graph, the denominator grows faster. And so when we're dividing by something that's bigger, we're going to get smaller and smaller, and we're going to taper off at 0. So the horizontal asymptote would be at 0. So that's sort of when the bottom wins, right? The numerator is smaller than the denominator. Let's come back to the middle one. Okay, so then at the bottom here, if the numerator wins, so if the highest power on x in the top is the biggest, bigger than the highest power on x in the bottom, that means that the top of the fraction is going to grow larger, faster, for really big powers of or values of x. So if the top grows faster and we divide, we're still going to have a really big number for y. And so y is going to continue to grow. It's not going to level off at any particular value. So in that case, we don't have a horizontal asymptote. Okay, and so even though I put this in the middle, the third possibility of these 3, right, is they tie. So maybe the highest exponent in the top is the same as the highest exponent in the bottom. In that case, it levels off at a different number, not 0, but something else. So the way we can determine what that is, I like to describe this in words. The book usually will describe this in symbols. Okay, but basically we're going to take the leading coefficient, the number in front of the highest power of x for the top, divided by the leading coefficient on the bottom, and that's going to tell us where it levels out. Okay, so here's an example so you can kind of make use of that. Let's see if we can fit it all on the screen. So here's our same function, right? We can factor and reduce and then find the horizontal asymptote, or we can do it at the beginning. It actually doesn't matter. It's the same for both. This one, like we said before, is not factorable. So I usually use HA as an abbreviation for horizontal asymptote. Okay, so notice in the numerator, the degree is 1, because I have x to the first power. And in the denominator, the degree is 1, because I also have x to the first power. Okay, so that means I have this scenario right here in the middle. They tie, right? They have the same highest power of x, the same degree. So the horizontal asymptote, I'm going to divide the leading coefficients. So the number in front of that highest power of x in the top is a 2. In the bottom, it's an implied 1 right here in front of x. So my horizontal asymptote is at 2. And this is the horizontal line that the graph approaches at the ends of the graph. So if we were to draw that in here, it would be right here, horizontal like the horizon, right? And it's the line y equals 2. So at the ends of the graph, this curve is leveling off and getting closer and closer, infinitely close to the y value of 2. Same thing on this side. Okay, so we've talked about the vertical asymptote, we've talked about the horizontal asymptote. You could definitely take some time to go look in the book and pull out some examples where you can test yourself, see if you can find the vertical asymptote, see if you can find the horizontal asymptote. It's good practice because those are going to be important skills as we start to integrate all of this together into making the graph for these functions. Okay, we said there were 4 if you count the domain, but categories. So the third one would be a hole or a missing point in the graph. I like to call it a hole, but some books call it a missing point. And there really is one point that is left out, where the original function is undefined. Okay, so if a rational function can be reduced as a fraction, so I can factor and cancel, the eliminated factor, whatever I cancel, yields an x value that's not part of the domain and causes an open hole in the graph. Okay, so let's look at an example of that. So I could take this function, I have x minus 2 over x squared minus 4. I could factor it. If I factor the denominator, let me go ahead and put this in parentheses. That's a difference of squares. Okay, maybe before I cancel, we should talk about the domain. Okay, so there are 2 values that are not going to work for this function, right? To find the domain, we'd have to set the denominator equal to 0. So what x values can we not have? If I set x plus 2 equal to 0, I cannot have negative 2. And if I set x minus 2 equal to 0, I cannot have positive 2. These are not going to work for this function. And you could try it. You could plug them in either place, and you're going to get something divided by 0, which is not good. Okay, so we're going to write our interval notation just like we have in the past. I know it's been a while, so I'm going to draw the number line picture here as a visual aid. We did this at the very first couple of classes in the semester, and it's been a while, so this is a good chance to review this idea. So negative 2 is left out, and positive 2 is left out, but any other number for x is okay to use. So that's going to actually divide up the number line into 3 regions, the left side, the middle, and the right side. So I want to write my domain with interval notation. I'm going to use D for domain just to save space. And I'm going to go from left to right. Because -2 is left out, do I want to use the square bracket or the round parentheses? Yeah, I want to use the round parentheses, right, to show that I'm getting infinitely close to -2, but I'm not including it. So I'll have the left side, the middle is included from -2 to 2, and the right-hand side, from 2 to infinity. So this would be the domain, right? Both these values do not work. Okay, they are not both wholes though. And for this problem, only one of them is a whole. So now let's do our reducing. So I did my factoring so that I could figure out the domain. Now let's reduce. I have x minus 2 in the top and x minus 2 in the bottom. Remember, I can only cancel 1 for 1. So even if I have multiples, I can just cancel 1 for 1, right? So now I'm left with this fraction, y equals 1 over x plus 2. So the graph of 1 over x plus 2 is the same as the graph of x minus 2 over x squared minus 4, except for the graph of the original function has a hole. Okay, so we're going to look at how to find that hole. Let me write, I didn't print the directions for some reason, so I'm going to just write them. Okay, so we want to sect the canceled factor equal to 0. We cancel out x minus 2. So I'm going to set that equal to 0. Add my 2 over. Okay, so x equals 2 is the x value of my hole. Now this is a missing point, so I'm going to draw it in as a little open circle on my graph. Okay, so I need both. It's two-dimensional graph. I need an x value and a y value. So this is how we find the x value. To find the y value, I'm going to plug in x, or plug x into the reduced function. Okay, I don't want to take my 2 and plug it into the original function because I have a hole there. That's why it's undefined, right? It's in my list. It doesn't work. But I can use this to get a y value of where it would be if it did work. Okay, so here's my reduced function. So I'm going to take my x value of 2 and plug it in for x. And that's going to give me the y value. So together, I have a hole at the point 2, 1/4. Okay, now for this part, we've just looked at the hole. So I have a couple more examples that I want to run through all 3 parts with you, and then we can make a sketch of the graph. We're going to start with this one actually, so we can fill in the rest of the gaps and kind of talk about it a little bit. Okay, so just like we did for the polynomials, I like to go one by one down that list. So I like to do the vertical asymptote, the horizontal asymptote, the hole, and then I like to make a sketch of the graph. Okay, I know we just did this, but let's factor this again. And reduce. Okay, so from here we can find the, let me put it over here, the vertical asymptote. If you look back to the directions that we jotted down for the vertical asymptote, we said we're going to factor and reduce. We just did that. Then we're going to set the denominator equal to 0. So our denominator here is x plus 2. Set that equal to 0. So I have a vertical asymptote at x equals -2. Okay, and I'll draw that into my graph in just a second. Then I can look at the horizontal asymptote. Remember, for the horizontal asymptote, we looked at that three-parted rule. Okay, where we compare the degree of the top versus the degree of the bottom. So in this example, the degree of the numerator is 1. Okay, and the degree of the denominator is 2. And okay, I looked at the original function. I didn't even think, you could have used this one as well. If you did this one, the degree of the numerator would be 0 because there's no x's here. It would be like x to the 0 power. And the degree of the denominator would be 1. Either way, the degree of the denominator is bigger. So if we look back at that three-parted rule, the top is smaller than the bottom, so that'd be the first part that we listed. The bottom's going to grow faster, so the horizontal asymptote is going to happen at y equals 0. It's going to level off at 0, a lot like 1 over x. And this is a lot like 1 over x. Actually, this plus 2 is just going to shift it. Right, so all those shifting ideas you could do here too. Okay, let me just add in the whole because I know we just did that. I'm not going to go back through it because we just did that, right? So we found that we had a whole at point 2, 1/4. Okay, so let's put all of this into a sketch. I'm going to move down, but we can always come back if we need to. So when we make the sketch, the first thing we want to do is put on our asymptotes. So we had a vertical asymptote at -2. Vertical like vertical blinds, right? It is kind of important that we get these going in the right direction. All right, and then we had a horizontal asymptote at y equals 0. So that's right on the x-axis. Okay, and then if you want to go ahead and plot the whole, you could do that. The whole was at +2 1/4. So that'd be right about here. And it's just a little open circle in the graph. Okay, so these dotted lines divide up the graph. So since the whole is here, we know that part of the graph is going to be in this region. Since it's a function, it's got to pass the vertical line test, which means there's not going to be anything in this region. And then the left-hand side is either going to be up here or down here. So we do need to plot a couple of points just to decide where the graph is. What's going to help us out a lot is that the graph is going to approach these dotted lines. I always put my vertical asymptote in the middle because I do have two sides of this graph and I want to make sure I pick points on both sides. So I want to pick a couple numbers smaller than -2 and a couple numbers bigger than -2. Okay, you could always add to this list. This is just kind of a good starting point. If this weren't enough, you could add if you wanted to. Okay, the easiest place to plug these in is to the reduced function, I'm going to go ahead and recopy this so you can see it all on the same screen. Don't forget it's 1 over, right? So if I plug in -4, -4 plus 2 is -2. It'll be 1 over -2, or -1/2. If I plug in -3, -3 plus 2 would be -1. It's 1 over that, which is -1. Then on this side, -1. If I plug that in, it'll be 1 over 1. If I plug in 0, it'll be 1 over 2. You can definitely use decimals if you like that better. Okay, so I'm going to start on the positive side just so that I can connect up with this hole that's hanging out over here. All right, so I have -1, 1, 0, 1/2. Now that's not a lot of points, but I know that it's going to approach the horizontal asymptote at the end of the graph, just because of what a horizontal asymptote is. And as I get closer to -2, it's going to shoot up to positive infinity and get infinitely close to the vertical asymptote. All right, on the left-hand side, I have a point at -3, -1, and -4, -1/2. Same thing, it's going to approach the vertical asymptote in the middle and the horizontal asymptote at the end. All right, I didn't go crazy with my t-chart here, but you could definitely add to this, and you could definitely use your calculator to help you out, and that's totally fine. Keep in mind that if you graph this function in your calculator, you're not going to see the hole. But if you go back to the original, then you'll see this hole listed in the table as an undefined point. Okay, let's do one more. We're going to go through the same steps just to give you a good idea of how these work. Okay, so first, let's factor this. If I factor the top, I have a difference of squares. So we have x plus 1 and x minus 1. If I factor the bottom, I need two numbers that multiply to be 3 and add to be -4. So -3 and -1 are going to work really good. You can see that I have x minus 1 on the top and the bottom, so I can cancel. Okay, now I can spend some time looking for my asymptotes and my hole. So for the vertical asymptote, we said we're going to factor and reduce, and then set the denominator equal to 0. So I'm going to have a vertical asymptote at +3. For my horizontal asymptote, I can use that 3-parted rule. The degree of the numerator, for whatever reason, I always go back to the original for this, but like we said earlier, you could use either one. Okay, I'm going to use the original this time just because that's what I like to do, but you could do whatever you like. So up here, it's x squared. The degree of the denominator, also x squared. So they tie, right? They match. So if you look back at that 3-parted rule, if the degrees are the same, then we do the leading coefficient over the leading coefficient. So all over the place here, we have implied ones in the numerator, the denominator, or if you were to look here, numerator, denominator. So the horizontal asymptote would be 1 over 1, which is just y equals 1. Okay, and then we need to talk about the hole. All right. If we cancel, we will have a hole. We canceled, right? If we don't cancel, there will be no hole. Okay? Does that make sense? So the canceling is what produces the hole. All right, so to find the x value, remember we're going to set the canceled factor equal to 0. In this case, that's the x minus 1. So the x value will be 1. To find the y value, we're going to take the 1 and plug it into the reduced function. In both places. Okay, so for this one I get 2 over 1 minus 3 would be negative 2. 2 divided by negative 2 would be negative 1. Alright, so I have a hole at the point 1 comma negative 1. Okay, so I want to take these three things and put them into my graph. I have a vertical asymptote at 3. I have a horizontal asymptote at 1. And then I have my hole at 1, negative 1. 1, negative 1 would be right here. I should also point out the hole is in line with the rest of the curve. It's never going to be like floating out in space somewhere. Okay, so make sure your hole gets connected up with the rest of your graph. It's important. All right, here's just so again, so we have it all on one screen. Here's the reduced function. And just like before, I like to put the vertical asymptote in the middle and choose a couple points around it. So 2, 1. I'm going to add an extra one since 1 is where my hole is. I'm going to add a 0 up here so I have 2 points with the hole. And then 4, 5 on this side. Okay, so if I plug these in for x, if I plug in 0, I'm going to have 1 over negative 3. So negative a third. If I plug in 1, 2 over negative 2. That sounds familiar. Oh, right, that's my hole. Right, so you might want to circle that just so you don't forget that that's the hole. Okay, if I plug in 2, I'm going to have 3 over negative 1. So that's negative 3. Then on the right-hand side, if I plug in 4, I'm going to have 5 over 1. And if I plug in 5, I'm going to have 6 over 2. So that's 3. Okay, so let's plot these. So I have 0, negative a third, maybe right there. And I have 2, negative 3. I could have gone even further. I think if I did negative 1, that's going to be my x-intercept because that's what makes the numerator 0. I don't usually make that an emphasis, but that sometimes can be a really convenient point. So whenever I set the top equal to 0, that's going to be the x-intercept. I'll just add that. I don't have it in my chart, but I'll add that in there. Okay, so I'm going to approach the vertical asymptote in the middle and the horizontal asymptote at the end. Notice again, my hole is in line with the rest of my curve. On the right-hand side, I have a point at 4, 5, and 5, 3. Same thing's true here. I could plot more points if you wanted to continue adding here, you could, but it's still going to approach these dotted lines. It's going to approach the vertical asymptote in the middle and the horizontal asymptote at the end. All right, this one went rather long, but I hope this gives you a good description about the rational functions and all of the characteristics that go into them. Good luck with this. We'll definitely have time to practice it in class together. All right, thanks for watching.